Okay, so we'll begin. Thank you very much for joining my session this afternoon on operational readiness and the commencement of caving operations at Oyu Толгой. So just before we get started, a quick disclaimer: this presentation is used for the purposes of supporting understanding of the technical aspects of Oyu Толгой, and estimates and forward-looking information provided in this presentation are based on assumptions and subject to uncertainties that could prove to be correct, and actual results may vary. So, touching on today's agenda, in this agenda today, we'll touch on a reminder, firstly, of the block caving method. We'll then touch on the OT block cave as well. We'll be looking at a safety share into the major hazards in block caving, which has been a popular topic over the last two sessions in the symposium. We'll also look at the operational and cave readiness aspects of OT, so in particular looking at our ground support completion in the underground mine, looking at our cave monitoring instrumentation, which we'll use to manage our critical risks, extraction level stability instrumentation, and also having a look at some of the operational readiness photos that we have from the mine. And we'll tie it all back at the end to how we manage major hazards at OT using all of that readiness criteria. So we'll start off with a reminder of the block cave mining method. This is a video on that method supplied by one of our contractors, Epirock Mining.
Block caving is a large-scale mining method that allows for huge volumes of rock to be extracted efficiently. However, the development time before production starts is longer compared to other mining methods. By drawing rock from the extraction level in the lower part of the mine, a gap is created. Absence of support for the overlying rock mass, together with rock stress and gravity, will cause the rock mass to cave. This minimizes drilling and blasting of ore, but require the ore body to be large enough and the rock conditions to be favorable for natural breakage. To draw the first pieces of rock, to create this gap, the rock mass in the lower part of the ore body needs to be broken down into smaller pieces. To achieve this, an undercut level is developed and blasted. Below, an extraction level is developed where ore will be extracted throughout the life of that production area. Drawbells are created between undercut and extraction levels and become passages for caved rock. To avoid misfires, accurate drilling is crucial. Substantial rock reinforcement, such as steel arches, sprayed concrete, cable bolts, rock bolts, steel mesh, and straps, are usually required due to several factors associated with block caving, including extreme rock stress changes and a long production period. Rock is loaded from the draw points and can be dumped into ore passes connected to a haulage level or directly into a crusher. A variety of transportation methods can be employed for transporting ore to surface. The fragmentation of the ore and the crushing requirements are key factors influencing the choice of a method. The extraction of ore will sooner or later cause the surrounding rock to cave, resulting in subsidence on the surface. Provided the rock breaks successfully and the ore can be extracted evenly at desired draw points, block caving is a high productivity method with low operating cost that allows a high degree of mechanization and capability of automation.
So moving on to the OT block cave, and we have seen this slide a couple of times in this presentation, just a reminder of Oyu Толгой and our first mining horizon, which is shown on the right-hand side, Lift 1, and our current operational readiness program associated with Panel 0, which lies in the middle of that lift. So just referencing back to that video, on the left-hand side here, we have the apex level, the undercut level, and extraction levels, which we'll discuss in more detail shortly. In the context of block cave mining, we've got a safety share here on the major hazards which we do control in underground mining. The first one that we're showing here is a fall of ground event, which is related to ground control. So the major hazard here is, of course, a section or a portion of the underground tunnel collapsing. Other major hazards we have in underground mining relate to the inrush of liquids. Shown here, there's a high pressure water source in the underground mine as an example. Inrush of solids is an event where dry or wet material flows from draw points, and the inrush of those solids can be quite violent and happen very quickly. The other major hazard event that we control in block caving is related to air blasts. So what you can see here in this video is a large air gap above a muck pile in a block cave. So that air gap has above it solid rock, which has the potential to collapse and compress the air inside that gap, which can force that air out into the rest of the mine. So how we relate that back to Oyu Толгой, we have a cross section here of our mine of a typical advanced undercut block cave. Ground control is related to the areas of the extraction drifts and undercut drifts. So where we have our tunnels in the underground mine, we control that ground with ground support elements. The inrush hazards that we looked at of water and dry and wet material, we control that through the draw points and the undercut rings to make sure that those events do not occur. When it comes to air blast management, we control air blast management with the cave monitoring plan, which controls the amount of air gap that we allow to occur inside our block cave. All of those major hazards are complemented and encapsulated inside what we call the cave management plan, which we'll discuss a little bit later as well. So in terms of operational and cave readiness at Oyu Толгой, we're focusing on 4 main criteria in terms of cave management and geotechnical engineering. The first of the criteria is ground support completion, and our requirement to start the undercut here is that we have our ground support complete within 100 metres of the execution point for the undercut. We have a requirement for geotechnical instrumentation to be installed, and this instrumentation is both surface instrumentation installed for monitoring the cave and the cave's performance, and we have stability monitoring instrumentation installed in the underground mine as well, with the same criteria of being installed within 100 metres of where the undercut will start. The cave management plan is the critical cave execution strategy document, which has been agreed on, endorsed and reviewed and signed off in readiness to commence the undercut. And we'll also be looking at operational readiness and making sure that the mine is operationally ready to start. So our first topic for discussion is ground support completion, and what I'm showing here are our 3 main levels on the OT underground mine: the apex level, the undercut level, and our extraction level. And the green colour indicates where ground support has been completely installed. So as you can see on all of our levels, the apex level, the undercut, and the extraction level, within a 100 metre shape around the initiation point of where the undercut is starting, which is shown there with the explosive shape. We've got the vast majority of the ground support completed in there. The last little bits of remaining ground support that we have to install are related to areas which are just completing mining as we speak. So that ground support will be complete very shortly. In terms of ground support execution, we're well and truly advanced on the apex level, undercut and extraction levels. What you can see here is a photo example of the ground support that we've installed on the extraction level. It's a very high capacity support system, a combination of sprayed fibercrete, mesh reinforcement on the outside of that, which is bolted with rock bolts at 1 meter centers. And on top of that, we have cable bolts and cable slings, which you can see sitting on top of the mesh. Moving on to the cave monitoring instrumentation that we have installed at OT. So looking at two separate photos here. On the left-hand side, we have a photo of the microseismic system that we've installed at OT. The microseismic system is installed to pick up very small seismic events, which are associated with the caving mechanics. This system has been completely installed, operational, and is currently reading seismic activity around the mine as we speak. On the right-hand side of this image, looking at a plan view of panel 0, you can see here the different shapes indicate another different instrumentation system. So the different shapes indicate open holes, cave trackers, and cave detectors, which we'll go on to discuss shortly. The green colour indicates that they are all installed and operational as well. So in terms of cave monitoring and the instrumentation that we've installed for cave monitoring, we are complete and ready to begin. So here's an example of how microseismicity occurs around a block cave. And the microseismic events are shown here in the blue dots, and the cave growing underneath it is shown in the grey colour. So as the cave begins to grow and draw continues underneath the cave, the microseismicity above the cave occurs, and that's where the cave will begin to grow. So on the right-hand side here, I've just shown a cross-section through the cave and the different zones which we'll be discussing. So the mobilized zone is the zone of material that is moving and getting actively drawn down to the extraction level. Above that, we have the air gap, which allows the yielded zone to fall into the air gap and then become part of the mobilized zone. What we saw here is the seismogenic zone, which is illustrated over here as this section on the right-hand side, and that is the zone that our microseismic system picks up seismic events. So the seismic events are the vibration that's felt when the rock fails in those locations. The other thing we're using for tracking the cave and how the cave is progressing is a system called Geo Foresight Markers, or cave trackers. We've got a picture here on the right-hand side of how these instruments tell us where the cave back is. So as the cave is growing and we enter that yield zone, the instruments will begin to move and twist, and that movement and twisting gives us an indication of where that yield zone is and where the top of the cave is. So how that actually looks in reality is we have the extraction level at the bottom. We have a series of instruments installed from the surface down to just above the extraction level. They're installed at regular intervals down that column, and as the cave grows from the bottom, those instruments will pick up where the cave is growing. So as the cave comes up, you see the instruments begin to move and tilt, and that tilt is picked up by these highly sensitive instruments, and that information is passed on to the geotechnical engineers. The other system we've installed to complement the Geo Foresight Markers is a system called the Cave Tracker. And the Cave Tracker is similar in some respects to the Geo Foresight Marker in giving us information about the cave back. What the Cave Tracker system also gives us is information about the flow of the material inside the cave. So as the beacons fall into the cave and they begin to move through the cave, those beacons are detected by a series of detectors around the periphery of the cave and underneath the cave, and they are able to triangulate where that beacon is inside the cave. And that gives us very good information in tracking how material is flowing inside the cave. So here's a video example of the information that we do get back from cave trackers, and this is information showing over time with respect to the cave, how they move down through the cave, and how we can pick that movement up and use that information to understand flow inside the cave. We'll also be installing a series of open holes from the surface to the cave. So the open holes are drilled from the surface locations down to just above the apex level. And those open holes, we then install a camera down that open hole and lower it into the cave. So you can see the camera winch on the right-hand side here. That camera is lowered down through the hole, which breaks into the cave, and we can interpret the cave back location and also the gap between the cave back and the muck pile as well. So some of the information or some of the images that we can get back from these cameras are shown on the left-hand side, where we can see the cave back location, so where the camera breaks through into the air gap. We can see when there's very little air gap void, and we can also see where there's the yield zone occurring, so dislocations or shifting inside that drill hole. Open holes are very important information for us in terms of cave backtracking. Here's a video of some of the kind of information we get from these drill holes. So you're looking down into the top of a cave here. So this is breaking through into the top of a cave. Draw was heavily occurring on the left-hand side of this video at this time, and it caused the material inside the cave to reel very quickly and move very quickly towards where we're drawing. So the open hole cameras give us very good information about our cave location and also the material flow in the cave as well. So tying it back to managing risk with our comprehensive systems that we have at OT, one of the major risks that we looked at first was the risk of air blast, and we've talked about that quite thoroughly in the last 2 days. We have our controls installed at OT to manage our monitoring of the air gap and the size of the air gap. So we have our seismic system, we have our markers and our cave trackers, and we also have our open holes to monitor and track the size of the air gap. Based on the results that we get back from the instrumentation systems, we will make changes if required to the production plan to make sure that we remain inside our air gap parameters that we have set up. We also looked at inrush of liquids and inrush of solids risks and how we control those at OT. So firstly, we have a very extensive ore body knowledge and drilling program, which has been extensively logged for both the rock type and water intercepts. So we have a very good understanding of our water risk at OT. We also have installed the flow markers, which give us excellent information of how material is flowing through the cave. And then we also have operational controls at the mine. So we have bunding controls and observational controls around making sure that the risk of inrush at draw points is managed, and if required, we make sure that we manage that risk by removing people and switching to automated loading and remote loading capabilities. So moving on to the extraction level now. So what you're seeing here is our multi-point borehole extensometer array across the extraction level. So this is instrumentation that we've installed on the extraction level to monitor how the tunnels are moving and converging. So the images that you see here are a plan view and an isometric view of the extraction level, and the green color indicates that the instruments are completely installed in those locations. So again, where the undercut is starting in the southwest corner of panel 0, we've installed all of the instruments that we require to have in place for that. In fact, we've basically installed all of the MPBXs right across the footprint, which is extremely good to have that information in place prior to starting. So what is an MPBX or a multi-point borehole extensometer? So what we're showing here is a typical array of the MPBXs that we have at OT. We'll have one in each wall and one in the backs. The MPBX is the blue instrument that you see there, and it has along its length 6 anchors in at different locations along the length of that instrument. We drill a hole in the rock, and that instrument is then inserted into the hole with a cable hanging out the end of the hole. Once the instrument is inserted into that hole, we then attach a grout tube into position, and we push grout into the hole, and that grout then anchors that instrument to the rock. So what happens after that is that as we get any loading onto the pillars or any cracks or deformation into the rock, as that rock moves, the rock will move the anchor with it, and we can pick up where the displacement is occurring inside that rock mass. So this gives us excellent information into our ground's response to our current mining strategy. So what I'm showing here is just some typical, a typical example of information we would get out of an MPBX. So this is showing the instrument down here in the red circle. And what you can see here on the graph is how this instrument has responded to mining. So you can see as after the instrument was installed, there was some slow creep occurring on this instrument. And as we began mining this tunnel very close to that instrument, we could see that the instrument began moving again. And it gives us very, very good information into our rock mass response to mining. Another thing we're doing on the extraction level in terms of monitoring is mobile laser scanning. So the mobile scanner that we have is deployed across our footprint levels, and you can see it there installed on the front of one of our underground vehicles on the right-hand side. And on the left-hand side, you can see a typical image that we get back after we've taken a mobile scan. So this is a scan of the tunnel underground, and all new scans that we take as the car drives through this tunnel are compared to the original scans that we had set up in place. And we compare the current scan to the old scan, and that allows us to pick up any changes in that tunnel's condition or any convergence in that tunnel. So we can monitor it in terms of displacements. So the darker colours or the warmer colours are showing us where there's been areas of movement in that tunnel. So the engineers can go and investigate why. So this next video is a video showing how mobile scanning is used to track deformation in a tunnel as the undercut front approaches geological structures or another access drive. So what you can see here is as the undercut is far away from this location, there's small amounts of convergence in that tunnel. As the undercut progresses forward, so after 2 months' time, you can see that the colours of the wall begin to change in line with the stress concentrations ahead of the undercut. And it's very clearly picked up in the mobile scanning here that those walls are beginning to close. After 4 months' time, you can see the convergence begins to increase more, and you can see convergence now begins out near that intersection and on that structure. So mobile scanning gives us a 3D image of change in that tunnel as the undercut moves, and it's very critical information for our geotechnical engineers to make decisions on in terms of our ground support and our rehabilitation strategies. So back to how we manage our critical risks with comprehensive systems in terms of rockfall. We've shown the ground support that we're installing has been designed to cater for our expected rock conditions. We have significant amounts of MPBX instrumentation installed through the footprint, and we also have our mobile scanning across the footprint to scan our deformations across the footprint as mining continues. So back to the cave management plan. So the cave management plan is used to define the strategies and plan used in the management of the critical caving risks of Panel 0. So this includes, but isn't limited to, the undercutting, the draw control, and the cave propagation processes. It defines and controls the major hazards associated with block caving that we've just discussed. The CMP also outlines the guidelines and rules which reflect the dynamic process of production performance over time. So this is from when the undercut is initiated right through the production profile and cave propagation through to a breakthrough. So the CMP is used with other Rio Tinto underground standards to manage safety in the underground mine. So the cave management plan does consist of three main sections, which is the undercut management, the cave propagation management, and the surface subsidence management. The CMP is a live document. This is important. So as the speakers over the last 2 days have explained, we learn a lot when we begin mining, and we expect to learn a lot from our significant instrumentation system at OT. We will make changes where required based on the information that we get back from our instrumentation system, and we'll use that information as well forward projecting into the other panels at OT. So here is a numeric simulation of panel 0 execution. So what you can see here in the dark grey is the extraction level, the light grey is the haulage level, the blue is the undercut starting and the development occurring behind the undercut, and you can see the drawbells in red being fired as well. So as we progress the undercut from the southwest corner up to the north, this is how our current undercut strategy and our drawbelling strategy occurs. I'll just play through that again. What you can see again is on the right hand side is the isometric view of that same video. So the dark grey is the extraction level, the light grey is the haulage level, the blue is the undercut as we begin to move the undercut across the footprint, the red is the drawbells that get established underneath the undercut, and the green is how the cave will grow as a result of our draw strategy as the cave progresses across the footprint. So this next slide is just zooming out a little bit to show panel 0 in the middle. So you can see panel 0 beginning to undercut, the cave beginning to grow, and as panel 0 finishes undercutting and the cave begins to propagate, panel 2 then begins on the left-hand side, and panel 1 will begin on the right-hand side, and that cave propagates through to the surface you can see in panel 0. As they near the surface, those caves will begin to come together near the surface and cause one big subsidence zone on the surface. So just touching now on operational readiness at OT. So what you see here is a photo of one of our long hole drill rigs on the undercut level, and this is currently or was drilling the holes in the undercut slot and the undercut rings, and this is in preparation to fire undercut. So that machine looks nice and new, but it won't stay that way for very long in an underground mining environment. But we've started the drilling process on the undercut. What we've also done as part of operational readiness is get some operational exposure to draw point development. So we've begun draw point development in a location underground, which gives us an opportunity to train the mining team in developing draw points and understanding the mining process to get through the draw points. But it also gives us an opportunity to train our construction teams as well in building and constructing draw points. It's a very important skill to get right, and it's very critical to our mine execution plan that it's done efficiently and as fast as possible so that we can extract the most value out of panel 0. So this is looking at the construction of our first truck chute, this is not required to start undercutting with panel 0, but it is our first truck chute and ore pass to support sustainable production. So what we've got here is a picture of that design of that ore pass in that truck chute. On the left-hand side, you can see the bottom chamber of where the truck chute will be situated, which is where the trucks will be loaded. You can see the steel cans coming through the roof there in the middle of that photo on the left-hand side, so just in this location. On the right-hand side, you can see what we call strand jacks, which are installed on the top of the ore pass, and these are used to lower those cans in place. So these cables that you see on the top are used to lower the different ore pass liners and segments into position and slowly lower them down and eventually grout that into position. So construction is progressing exceptionally well on the truck chute as well. We're also making very good progress on the concrete roadways on the extraction level. So you can see here the concreting of the floors. This is important for high-speed production out of our loading fleet to make sure that they've got a nice smooth roadway to move fast and efficiently on as they draw from the extraction level. So the concrete roadways are going well as well. So just circling back to our operational and cave readiness program, we discussed these at the start of the presentation. So in terms of the ground support completion, we're ready. The ground support is installed in the areas that we require it to be to start undercutting. In terms of the geotechnical instrumentation, all of our surface and cave monitoring instrumentation has been installed and commissioned and ready to begin. Underground, our stability monitoring instruments have been installed and are ready to go as well. Our cave management plan, which is the document used for effective execution strategy, has been agreed on, it's been signed off and endorsed, and that's ready to go. And we've just shown in terms of operational readiness, the mining teams and the construction teams are also ready. So I'm completing my slide pack around the operational readiness at OT. We're ready to go. So thanks everybody for your time, and look forward to some questions. Thank you.
Thank you, Glenn. So I hope that you give a lot of assurance to those people waiting what is happening at OT. So you just mentioned about those new technologies and those state-of-the-art equipments you are installing it at OT. So we have a couple of questions from attendees. So I would like to cover some of them first now, because some seems like some of our attendees listening from the cases or experiences from other operations, then thinking about whether it is comparable to something we have at OT, etc. So, for example, at our first presentation, we heard about caving rule and how important it is. So one question is about what is caving rule? Is it similar to trigger action response plan, what is implemented at OT? So please explain us if it is same or different.
Yeah, so our rules that are set up for our undercutting and our caving processes at OT do have tarps set up against them. Yes, so our rules are actually in place so that we actually execute the correct strategy. So the rules that we have in place dictate our undercutting strategy, it dictates our draw control strategy, and it also dictates what we need to do when changes occur. So with every one of those rules, we have tarps set up against them. So tarps are set up for managing air blast, tarps are set up for managing ground control, tarps are set up for all of the major hazards that we deal with on the mine. And of course, under those tarps, they need to be approved and endorsed by competent people, and then we use them as operational controls. Yes.
Okay. Second question is about this operational readiness and specifically about cave management plan. So So it seems like initially cave management plan is a plan implemented or applied during the caving. But according to your presentation, this is something you start preparing much earlier than the first blast of drop well. So
Yes.
when this cave management plan actually starts and how it matures along the way?
Yep. So the cave management plan, the version that we have at the moment, is the plan that's been set up around all of our analysis that we've done. Okay, so all of the ore body knowledge programs that we've done, all of the simulation work that we've done on the mine, how we've used the engineering practices to put those things into place. The cave management plan right now is based on the study work that we've done and how to execute this mine into in terms of how the analysis has been done up to this point. As we start the mine, as you correctly point out, we will learn more. And this is very important. So we'll learn more when we undercut, we'll learn more when we develop, we'll learn more when we draw. And as we learn more, that significant instrumentation program that I showed you for cave management, which is the cave instruments and the instruments on the extraction level, will tell us how the mine is responding to our current strategy. If we have to change something, then we'll do so in accordance with the data. Okay, so it's very important to learn as we go and apply our learnings as we go. What we know for certain when we start is that we will learn a lot about OT and how we learn those lessons and apply them in the future development, so panel 1 and panel 2, but also apply them in panel 0 for the remainder of panel 0. We need to do so. And the cave management plan will change and evolve over time. So the one we start with now is what we begin the mine with, but it will change with time, yes.
Next question is from yesterday's experience or presentations. We heard that the caving behavior is different when the caving starts or the initial undercutting begins. But when the operation is in steady state, then the behavior will be totally different. So you have lots of these instrumentation equipments and monitoring equipments. Those will start giving you feedback in early days of undercutting. So how you adjust if those instruments are giving you those feedbacks, but it is not expected to this steady state level, but something different. You just accept it because it is undercutting early days, or you need to analyze it and start looking at it?
Yeah, no, it's a very good question. And when we will be analysing it from the very beginning. So the reason for putting in all of this instrumentation is so that we capture the data as soon as possible, and we can analyse the data as soon as possible, and if required, make changes. In a perfect world, everything goes to plan, and we execute the mine the way the cave management plan says. The ground responds the way the cave management plan says, and everything will go great. And that's what we all are absolutely hoping for. If there are changes to the way that the undercut performs or how the cave propagation performs, then the instrumentation is put in place so that we can manage that. We can make decisions, the best decisions for the mine in terms of safety, but also productivity. And that's the integrated approach to these systems, is that they provide the information that engineers need to make very quick decisions in terms of safety and production.
Good. There was one animation you showed about how the caving will propagate in between panel 0, 2, and 1, and that numerical modeling shows that when the caving is going up, then there will be a convergence between those different blocks. Mm-hmm. So as a result of that, actually the pillar between those three panels, those two pillars, will be not that high. Actually, it is somewhere, what is it, 50, 100 meter or something?
Yeah, so what's actually happening in that simulation is as those caves are propagating up towards the surface, as they grow, they will eventually begin to widen and they begin to interact. So it's actually the boundary of the cave that touches each other, but the material moving in the middle of the cave doesn't actually move above those pillars. The material that's moving is only above the extraction levels and those draw points. Okay, so as the caves begin to join, as they move up the surface, that's just the boundary of that solid material. The material that's moving inside those panels is still directly above the extraction levels.